By the way, to everybody in the participants, I'm gonna try to look at your questions on Zoom, but if I miss something, maybe talk to Jamie or something. I will try to answer everything as you go. You don't have to wait till the end to ask questions. You can interrupt me as you wish. In fact, I hope you will interrupt me.
Yeah, I can monitor the chat, and if you miss anything, and somebody doesn't jump in, I'll try and jump in and make sure.
Do you want it to be relevant to the talk, or are you just hoping for interruptions in general?
I'll leave that up to you.
Okay, cool.
Oh dear. Okay. All right, I'll just start because it's at this point we can just introduce the lecture. So welcome everyone. As I told Ramesh, you'll probably be sick of me. You have 4 hours with me. I hope to make it interesting and fun and painless, but if I fail to do that, I do apologize in advance. So I think it's a good time to talk about black hole uniqueness in view of what's happening both at the BHI and at a wider scale. And I sat in too many talks, holding back some kind of frustration when I would hear what people would say. So I thought it was time to settle the scores, and really just so I can just get it all out in one go, and then we can move on and be nice. So 4 lectures. So in the first one, it's just basics. So for those who need sleep and who already know all this stuff, you're welcome to doze off. Lecture 2, we're going to go in the past and look at the golden oldies. So these are the classics of the 60s and 70s. And many physicists and astronomers seem to be traveling in a time machine because when they talk about black hole uniqueness, they're actually still back in the 60s, 70s. I don't know if they have access to Kerr and they've jumped in or something, but certainly they're stuck there. So we'll go back and we'll revisit the golden oldies. Theorems by Israel, Carter, Robinson, Hawking, etc., that are taken by physicists to kind of be the last word on the subject. Then in lecture 3, we'll talk about the modern work, and that's happened all within the last 10, 12 years. And we'll talk about the curse of analyticity, which is truly something that gets swept under the rug. And finally, in lecture 4, we'll talk about the state of the art, where we stand, and I will try to parrot some of the bits of wisdom I've been able to collect from leaders in the field. Conversations with people who have worked on this or who have a much sharper intuition about these things than I do. And I should also say that I am an outsider in the sense that I have not worked on black hole uniqueness and I have not proved a single theorem in the field of black hole uniqueness. So I'm certainly an outsider. Okay, so let's begin. So as I told you, the basics are going to involve a little bit of boring stuff that I have to sit through with you, and then we'll talk about some slightly more interesting things towards the end. But let's first start out with what is black hole uniqueness? And what is it supposed to be in particular? So the first point is that it's supposed to capture the idea that stationary vacuum and asymptotically flat black holes are Kerr or Schwarzschild. So I'll just say Kerr because Schwarzschild is Kerr with trivial A. And practically, the uniqueness is to be used by astronomers and physicists, astrophysicists, to justify using Schwarzschild or Kerr as a template to observations. So Rashan gave a beautiful talk the other day about constraining both in theory space and then within GR, what kind of metric, etc. One can infer from observation. And so, but the backdrop of all of that is the idea that these parameters, these Schwarzschild and angular momentum and mass parameters are lurking in the background as things you can rely on. And then the reason that the uniqueness theorems got the kind of street cred and reputation they got is a historic reason, and it's this no hair propaganda, right? Which is a term coined by Wheeler, I think, but Eric knows these historical bits better than I do. But I think this was Wheeler. And this really captured the imagination. I mean, isn't it so nice to not have to think and just everything is Kerr or Schwarzschild? But what's usually missed is that the golden oldies, right, rely on assumptions, on unreasonable assumptions. And unreasonable meaning this means shouldn't be expected of nature. And we'll go through in much more detail what that means and what I'm saying here. But that's the basic history. And then something that's also tends to be missed is that oh, there's something in the chat. Bekenstein, Ward, and Garrosh have told me independently that nowhere is due to Wheeler indeed. Okay, good. So it is Wheeler. Thank you, Eric, for the clarification. So we'll, a large amount of time is going to be spent on what this thing right here is doing, right? I'm going to talk a lot about this particular link. The other thing that's also missed is that these uniqueness theorems, right? They are theorems. They just rely on certain unreasonable assumptions. Those theorems don't hold, even under those unreasonable assumptions, when you change one of the assumption, which in particular is the vacuum assumption. So when you drop vacuum, there are many solutions which have hair. So there shouldn't be expected of nature is, in a way, it manifests itself in two ways. The first is that nature contains matter fields. And the second is that even in the vacuum case, there are these unreasonable assumptions. And I'll discuss what these are. And for the mathematician, the main challenge has been to turn these into reasonable assumptions. And that's been the math challenge which is still unsolved. Okay. All right. I think that's just some preliminary remarks. I'm going to change gears somewhat and bore you through, I hope, less than 15 minutes of definitions, just so we are all in the same we're all in the same room. So my apologies to those who have seen this a million times.
Say group of deformations.
Diffeomorphisms, yeah. I'm writing these down. I'm doing this because I've noticed that in talks sometimes people just put text on screen, but I find that it's overwhelming. I mean, you have a voice and you have them, things to read. So I'm writing things down and just trying to go as slow as possible. And hopefully these definitions, I'll talk a little bit about them, and then together they will lead to a nice picture. So the first is that of a killing field. Okay, so I'm sure you've all seen that. And then the second one is just about what it means to have a conformal embedding. Yeah, so you have a one parameter group of diffeomorphisms from L to L. L is the manifold. And then you say, and it's generated by a vector field. So the map that takes L to L is generated by a one parameter group. So if it's a vector field, say T, it's X subscript T. A tensor is invariant under phi if its Lie derivative vanishes, and then if the metric has this property that its Lie derivative vanishes in the direction of X, we say that X is killing. And then the second one is basically when I change the metric by a conformal factor, omega squared, then if I can find a conformal isometry, so a diffeomorphisms that preserves the metric up to a conformal factor, such that the L is a subset of another manifold L bar. And I'll give you an example now of this in motion. And I'm doing this, by the way, because people use this term freely, but it's actually a subtle thing. So what's the classic example of definition 2, right? The classic example is Minkowski space. So Minkowski space looks a little like this, right? This is what Minkowski space looks like. But in reality, there's another space-time called the Einstein static universe. And Minkowski space in the Penrose diagram is often drawn as follows. Okay. These points are typically labeled I0. This is typically labeled I plus. And this is scribe plus, scribe minus. And the idea is that the Penrose diagram, which you're all familiar with, captures the global properties of this space-time. Now, the reason I draw it is because to actually make this notion of conformal at infinity precise, we need to, well, we're doing it via this definition, which means that we're embedding it somewhere. So I ask you now, what is the embedding of this Penrose diagram? What's the space-time that it's embedding into? And the answer is the Einstein static universe. Okay, so you can see that when I take this guy, I can embed it into here. The Einstein static universe is a cylinder space-time, and Minkowski has been wrapped into it. And the reason that this example is important is because when we define, I'm going to define now asymptotically flat. And the point is that I can only define asymptotically flat if I say that when I do a conformal embedding, I resemble this picture in Minkowski. That's how asymptotically flat is actually defined. People say, far away, you look like Minkowski, but that doesn't mean anything, right? What's actually happening is that first, you have to find a conformal embedding. This is this definition. Then this conformal embedding has to be such that the global properties and this kind of the nature of the conformal embedding resembles what you can do for Minkowski.
Hi, Martin, just to interrupt, there's a clarificatory question in the chat.
Yeah, L bar does not have a bigger dimension. It can do, but it doesn't need to. But thanks for the question.
Well, I don't understand what it means to be like Minkowski in the sense. I mean, so you have a transformation that goes from this more complicated space to the flat space, and it's within a conformal transformation of flat in the original space. Is that what
Yeah.
And so that it resembles Minkowski insofar as it's just a conformal transformation away from Minkowski in the source.
No, so it resembles Minkowski in the sense that so I'm going to write the definition down, but the point is the point is when you do this conformal isometry, this factor omega is tending to 0, which means that the distances between things is getting to 0, and which is why I can draw it on a piece of paper, right? Because it's actually the metric in Minkowski is not going to 0, so things are infinitely far away. But because things are going to 0, I can patch it onto a piece of paper, and then I can draw a boundary around it. And this boundary in the Einstein static universe is actually just a subset of the space-time. And so when I say like Minkowski, I mean to say there is a conformal factor which squeezes things to 0, which enables me to patch it as a subset into a bigger thing. And then when I think of the closure of the image of this embedding, it has exactly the same causal global properties as this particular example. Right? That is what asymptotically flat actually looks like.
So the fact that the Einstein universe is periodically repeated.
Yeah.
One axis is irrelevant because omega is 0. Is that the point?
The Einstein
These
stuff.
are not the same in terms of that global topology.
That's right. That's right. They're not the same because in here the Cauchy surface is just R3, whereas here the Cauchy surface is something closed.
Yeah.
Exactly.
That is irrelevant.
It's irrelevant.
Because you have shrunk the scale.
That's right. What allows me to do this map is that there's a conformal factor squeezing everything to 0.
Okay.
So why do I bother with this definition? Well, because it's going to actually allow us to define asymptotically flat, and that's what's going to be in the theorem. So
I think there's another question.
yeah, there's another question. One sec. Let me write the definition. I'll come to the question. By the way, if you're thinking that I'm being a little too careful and I should speed up straight to the black holes, the reason I'm doing this is because this will bite us in lecture 4. You will remember. I will remind you. I will remind you. So by the way, this would be L bar and this would be L, right? The L is embedded into L bar. So the boundary of L in L bar is this guy. Right. Apologies to those who can't see the blue. All right, but this is the boundary of the image under this map. Okay. So when I write the boundary of L, I mean something like this, the blue line. And then given that I have this embedding now, I can say that the metric in a neighborhood, the metric and other properties, the metric plus other things, typically I just mean other properties of the metric other than just the metric itself. So here when I say the metric, I mean everything. But when I say metric in general, the way people use the term is they just think of C0, so just distances. So when I mean other things, I mean the C1 properties of the metric, the C2 properties of the metric, etc., etc. Resembles Minkowski.
Sorry, what's the word in a something around here?
Yeah, just go home with cost neighborhood.
A neighborhood?
Yeah, neighborhood, sorry. Yeah. Yeah, so I use these things like neighborhood or DFM is all these kind of acronyms. Okay, there is a question in the chat I missed. So you may want to remark that I0, which looks like two separate points, it actually isn't, it's mapped to a single point in the Einstein static. Yeah, absolutely. So if everybody could point to the chat, that's Eric's made a remark here, that's totally correct. And yeah, so these
another clarification.
Yeah.
So would you call del L the conformal completion, or would you call L bar the conformal completion?
Yeah, L bar is the conformal completion. Well, really the conformal completion is L subscript, so the closure of L as a subset of L bar. Because L bar could be bigger, much bigger, right? Yeah. Okay. So now we have asymptotically flat, we have conformal embedding, we have asymptotically flat, we have killing, so it's time for stationary. So let's do it. An asymptotically flat spacetime is stationary. Or I should say, sorry, is asymptotically stationary if it admits an asymptotically time-like killing vector field. So VF is vector field. And then
You've already introduced the killing graph.
yeah, but last time I just said it was a killing field. Now I'm telling you it's time-like.
Fact is time.
Not just that, the fact that it's time-like in a neighborhood of infinity, asymptotically time-like, right? As you know, the Kerr geometry is wacky when you get closer, and it's no longer time-like, the time-like killing field. So the reason I say asymptotically is because there could be killing fields which fail to be time-like, but at least at infinity it's time-like. We're mathematicians. We like to quibble. So a domain admitting nowhere vanishing killing field is called strictly stationary. Time-like killing field. Okay. So now let's do static. Because
I have a question.
yeah,
The first is on the top line.
Yeah.
Could you have like an asymptotically dynamic vector field that is then, but in the interior you don't have not just the fact that the same killing vector field is not time-like, but just no killing vector field at all in the interior. Could you patch things?
Yeah.
So you can get that.
Yeah.
Okay. So and the other thing is in the second definition.
Yeah.
The fact that you have an outer surface where you have vanishing time-like killing vector fields
Yep.
at that point. So this means Kerr is not strictly stationary.
Correct.
Thanks.
Sorry, I'll get it to or I'll.
So this next one is static. Let me go back to it. So static means it's stationary, but moreover, there is a space-like hypersurface orthogonal to the orbits of the isometry generated by the vector field. And so the picture, and so in particular, Schwarzschild is static, but Kerr is not. Right. So in Schwarzschild, the Penrose diagram, I'm cheating here because I'm drawing a Penrose diagram I haven't defined for Schwarzschild yet, but we'll get to there in a minute. But for instance, this slice here and this vector field here would be an example. And then in Kerr, what happens is that because this guy is rotating, because there is this axis of symmetry, what happens is that it could be orthogonal here, right? You could find such an orbit, but as soon as you move out, because of essentially frame dragging, the next vector, the intersection with the flow of this vector field will now look like this. And this is no longer no longer the right angle. So this is now not orthogonal. And in particular in Kerr, you cannot find a surface for which the intersections will be all orthogonal. And in practice, by Frobenius's theorem, this definition can be checked by computation by computing the following thing. So this is equivalent to static. Many of the difficulties in Kerr, Kerr is very complicated for many reasons, but certainly this is when we start to see distinction between Kerr and Schwarzschild. Okay, and finally, my last bit of boring definitions before we get to some cooler definitions is axisymmetric. So a space-time is cyclic symmetric if it is invariant under the action of one parameter group SO2, and it is axisymmetric if the fixed point set of the action is non-empty. So the classic example is just this is the fixed point set of pi. Now you might ask me, why did you bother writing cyclic symmetric and then axisymmetric? Isn't it obvious that if you're cyclic symmetric, you're going to be axisymmetric? Well, yeah, but the point is that axisymmetric means that the fixed point set is in the space-time you're considering. So if I consider a patch of Kerr that's, say, a donut shape outside the horizon, I'm missing the axis of symmetry, and therefore I'm not axisymmetric, I'm cyclic symmetric. And this distinction will come to bite us in lecture 2 and 3. It won't bite us, it'll just rear its head. Now,
You mean if the slice of Kerr is not parallel to the
just
equator, so to speak?
no, just if it doesn't contain the axis of symmetry. So yeah, something, yeah. Finally, a space-time is stationary and axisymmetric if it possesses these symmetries, so let's say sigma t and chi phi, and they commute. Okay, so what this means is that you can do a rotation, then a time translation, or a time translation, then a rotation, you end up at the same thing. So in the asymptotics of Kerr, but not everywhere inside, this is satisfied.
Martin, another question.
Yeah.
On your previous slide,
Yeah.
so if you were to look at Kerr in Cartesian Kershel coordinates, the singularity is not at r equal to 0. And the axis of symmetry would pass through r equal to 0. But if you were to look at Kerr and Boyle-Lindquist, the singularity would define to be at r equal to 0 and theta equal to pi by 2. So does the axis of symmetry does it require you to already pick a gauge or like a coordinate system, or
No.
the quantity?
So
the-
yeah, it doesn't.
And so the fixed point set can change under.
Yeah, it can be in different places in different coordinates. Yeah. It can be identified by different equations in different coordinate systems. Yeah, absolutely. Okay. At this point, you will forgive me. I will have to just take a very quick break and I'll be right back.
Some definitions are new to me. But stationary, axis symmetry, they're all equal and similar.
Yeah, so you would even split further here. There's some thing called non-circular space and where if you are static, you are not necessarily even axisymmetric.
I see, okay.
Yeah, axisymmetric just means that definition. Static means that definition of the time that you do a simple time. Xi which d xi equal to 0.
It doesn't have to be spherically symmetric.
Not necessarily.
So what is so stationary just means you can be a stationary observer, right? Like you can, there exists like world lines you can be on where like you can translate into life and everything still is the same. But what is static? You want to talk about it.
Sorry about that. So these ones, I'm almost embarrassed to include them, but please accept my apologies. We say that a spacetime is a black hole if the boundary of the past of the future component of scry is non-zero. So I'm not going to draw a picture because you've seen it many times. And we just say that the event horizon is defined by the intersection of this boundary. Okay. Now let's do some examples because nothing is worth anything without examples. Okay, so we come to our favorite examples. Okay. So let's talk about Schwarzschild. Forgive me, because I'm sure you've seen it 100 times or more. So it's vacuum, spherically symmetric. It's also static. And it's also asymptotically flat. So Schwarzschild, the reason I say this is because Schwarzschild satisfies everything we've seen so far. The coordinate extensions reveal the following Penrose diagram. We can identify this as scry plus, scry minus. This is the event horizon. And then the black hole region is this thing. And all the definition, the reason why I mention it is because all the definitions we've seen are showcased in this example. And then we can even draw what I find sometimes a slightly more useful representation, even though it's kind of, morally speaking, kind of incorrect. But I like to expand my I plus and turn it into, say, an actual locus where you can end up as an observer outside of a black hole. The problem with conformal diagrams is that whilst they're very helpful, they also squeeze everything down to a point, which is, I think, unhelpful at times to understand and visualize. So this is the event horizon. The horizontal slice would be something like this. Okay, so this horizontal slice. That's that. And then the reason I draw this is because the endpoint, this is an observer traveling along a time-like geodesic. And so their past light cone is here. And they can stay at a safe distance outside a black hole. And then the endpoint of null geodesics is scry plus. Of course, this diagram is not faithful because if I shoot a null geodesic from sufficiently far up the curve, I seem to hit the red region. I'm simply drawing it because I think it's helpful when we look at Kerr later. So let's do the same for Kerr. So Kerr is somewhat more complicated, but it's helpful to see this. So let's talk about Kerr now. So again, Kerr instantiates all the definitions we've seen, and that's why I mention it. So it's vacuum, it's axisymmetric, it's asymptotically stationary, and it's asymptotically flat. In the sense that I've described precisely. I'm not going to draw the metric for you, but I would simply wish to point out this picture that I promised. So again, this is my idiosyncratic representation. You won't see it like this in the textbooks, but I find it helpful for my own sake. Okay, so what's happening here? So this is the red region that we saw in the previous, in the Schwarzschild picture. So this is the kind of the endpoint of all the time-like trajectories that go on forever in the exterior. This is the event horizon. And this is the boundary of the ergo region. And the reason is that if we draw a light cone here, we'll see that the light cone is bound to be contained within the event horizon. But what happens is that you can have trajectories that go in and then come out again of the ergo region. And so those light cones are, pictorially, we can draw them a little fatter.
Is the ergo region significant mathematically?
Yes, it's absolutely significant mathematically. It's what will come to bite us, and I mean it this time in lectures 2 and 3 and 4, because it's exactly this ergo region that screws everything up in the proof.
The proof of
The proof of the intended, no hair or uniqueness conjecture. So this ergo region will lead to a phenomenon that we will call trapping, trapping will absolutely screw us in the proof, and it will be the main thing that we will fight in the proof again and again. And in fact, the best state-of-the-art theorems available by modern mathematicians in this field have to assume conditions about this ergo region to really prove anything. So this is an absolutely crucial piece of the puzzle, and this makes Kerr very difficult and very interesting.
So Martin.
Yeah.
In this future stuff, those rings.
Yeah.
What's between the event horizon and the ergo region? Are you saying no time like?
Yeah, so
paths
these,
will reach there?
yeah, so sorry, so I was going to finish the picture. So this region is infinity, but it's infinity that lives at a finite radius away from the black hole, the event horizon. So I just distinguish these regions because, you know, in the red, you could move arbitrarily far away from the black hole, whereas in the purple, you're confined to a given radius.
But you can reach those points.
Yes, you can reach those points.
With time
With time-like
like.
curves. Yes, yes.
Okay.
I'm sorry, I just need a quick clarification.
Yeah.
So why can't you leave the ergo region?
You can.
Okay, sorry, I think I misinterpreted the lesson.
No worries. Yeah.
If you leave, you reach the red region.
Yeah, I figured.
Yeah,
I certainly hope you leave the ergo region.
Yeah.
Rather important.
You certainly can. You certainly can. It's just it's useful for illustrative purposes for me to distinguish these regions.
Sure, I guess, but why is it trapping then? If you're not really-
It's called trapping because null geodesics. So you're right in pointing out that there's two notions of trapping, and you're totally correct and on point to pick up on that, right? There is something called trapped, where we're talking about the first derivative of the area that's swept by null geodesics that are either outgoing or ingoing from a given surface. And that's what we mean by trapping, or trapped sphere, for instance, trapped surface. This phenomena of trapping is defined differently, and you'll see it in lecture 2 and 3. It's just defined in terms of null geodesics, which are forbidden to surpass finite distance from the black, that are fixed at a finite distance from the black hole.
I see.
So null geodesics that orbit around the black hole, basically.
Sure.
The photon shell that you discussed last time. That's what the mathematicians called these trapped null geodesics. Trapped to within a given region, but not necessarily a trapped surface. So there is some. Say again.
They can be perturbed out.
Yes.
Yeah, I see. Right.
Yeah. A perturbation could cause them to leak. Yeah. Okay, so at this point we have 7 minutes because we need to leave a bit of time. So I wanted to just give you the rough picture of where we're headed in the next few hours together. So I'll give you the rough conjecture, rough statement of the conjecture. When I say theorem or conjecture, I will always be referring to this flagship thing we're trying to prove. So everything is smooth. So G is in C infinity. And you know, we are in a vacuum setting. So Ricci of G is 0. Without these conditions, what I'm about to write down is known to be false, right? It's not like maybe it could be true. No. It's known to be false, right? Okay. So the conjecture says something like LG is asymptotically flat in the sense that we've seen. Its event horizon is non-zero. So remember, asymptotically flat will allow you to define event horizon because of null infinity. It's asymptotically stationary. That's key. And then we're going to add some extra conditions here. extra. I will explain what these are later. I don't have time to go into them. And then we will have either 4 or 4 star. So 4 is going to be more extra conditions. And 4 star is going to be the golden oldies, and which is going to be an analysis to the assumption. Then G is isometric to member of the family. Okay. So this is a simple form of the uniqueness conjecture, and 4 star is what's known, and this is the golden oldies that we'll talk in the next lecture, and I'll explain what 4. So 4 is this is modern work. This is the golden oldies. And we'll spend a lecture each on these. In lecture 3, I will try to convince you that the golden oldies analytium assumption is completely insane. And in lecture 3, I will tell you why the modern work falls far short of the desired statement that was hinted at by the physicists. And I will even discuss what some mathematicians believe, not just wacky, kooky people, but actually people at the very top of the field. They believe that, in fact, this could be false. So we'll go into that, and I will unpack what I just said in the coming weeks.
I
Yeah.
understand this. So when Wheeler talked about the black hole having no hair,
Yeah.
he surely meant that he didn't mean like accretion disks have no hair. Accretion disks are very hairy.
Yeah.
They're like all sorts of physics and special circumstances. So why couldn't Wheeler Redivivus say, oh, so if there's a problem in the ergo region, but that's not really part of the black hole itself, it's outside the horizon. So the fact that there's hairiness there, that doesn't really affect what I, Wheeler, want to defend, which is the in the immediate vicinity. I mean,
No. So there, no. I mean, the way I see it is as follows. These solutions were found, right, in earlier part of the century, and then in the 60s. Then very soon after, there were some theorems that showed you that under some conditions, and we'll go into this next time, you have to in fact be those solutions, and they are the stationary vacuum. The assumptions of stationarity and vacuum are crucial and would rule out accretion disks, which certainly would involve hair. Wheeler thought of a phrase, I'm not certain on the history of who came before what, etc., but he saw these theorems come out, and he was like, black holes have no hair, in the sense that anything that's stationary and vacuum must be one of those reference solutions. He wouldn't have meant to say that spacetimes which have accretion disks that are modeled in them have no hair. And he wouldn't have meant to say that this was a distinction between ergo, non-ergo region. This was purely a vacuum statement. And I think what he had in mind was that he thought that the theorems aforementioned were somehow, indicative of something truly significant. In particular, that this was true of all of these space-times that are asymptotically flat, asymptotically stationary, vacuum, and smooth. What I'm going to talk about is the fact that what he was working under was a set of assumptions which are not realistic. And moreover, that the modern work which does this has to still assume a bunch of things which we would like to get rid of.
So are these things going to be like decay rates? Is that the sort of assumption?
Not really, actually. The decay, the major assumptions that the state of the art work involves is stuff happening in the ergo region.
yeah, we have to.
Yeah. All right. Well, thank you, and I hope you join me. I hope I didn't bore you enough that you'll join me for lecture 2. I promise it'll get more interesting.
Already interesting.
Sounds good to me.
Thanks, Martin. I hope I'll be testing negative and able to join in person next week.
Oh, thank you so much. And we wish you a speedy recovery.
Thanks.
Bye bye, everyone.